Welcome everyone, my name is Piero Rivera Benois. I work in the signal processing group at the University of Oldenburg. Today I am going to present you our latest results on the sound pressure minimization at the eardrum for in-ear ANC headphones using a virtual sensing technique. The outline of today is going to be the following. First, I'm going to give you an introduction into the topic of ANC headphones, followed by a general description of how virtual sensing algorithms work. Third, I'm going to describe the proposed procedure that we use to optimize a fixed feedback ANC controller when we only have an internal microphone at this position by assuming an FIR filter structure for the controller and applying a virtual sensing algorithm called virtual microphone arrangement. Fourth, I'm going to present the simulation results that we achieved by means of acoustic transfer functions measured with a real device and a dummy head. Finally, I'm going to finish this presentation with a summary of the most important findings of this work. ANC headphones aim at minimizing the environmental noise at the listener's ears. These devices combine the passive attenuation achieved by the construction materials of the headphone and the active attenuation achieved by means of ANC. While passive attenuation is mainly effective in the mid and high frequencies, ANC is mainly effective in the low frequencies. At the right-hand side, you can see a typical in-ear headphone. It is equipped with an external microphone, an inner microphone, and a loudspeaker. The wave of incident noise first arrives at the external microphone as X, then travels through the device until it reaches the inner microphone as R, and finally reaches the eardrum as D. Simultaneously, the ANC controller generates the signal U to drive the loudspeaker, aiming at generating a sound wave that destructively overlaps with the sound wave of the incident noise. ANC approaches using the time-advanced external microphone signal X to generate the loudspeaker signal are called feed-forward approaches, whereas ANC approaches using the inner microphone signal instead are called feedback approaches. When an inner microphone is available, feed-forward approaches can also exploit the inner microphone signal to optimize the controller during control. Since the sound pressure at the inner microphone and the eardrum cannot be assumed to be the same while ANC is on, virtual sensing algorithms have been proposed that aim at minimizing the sound pressure at the eardrum. Virtual sensing algorithms work using a two-stage approach. In the first stage, called the calibration stage, an audiological probe tube is placed at the eardrum, depicted here in pink. With the DSP depicted in blue, the loudspeaker to microphone acoustic paths are measured. Afterwards, subject to the noise sound field, the microphone to microphone acoustic paths are measured. If a fixed controller is considered, now it will be optimized, considering the measured acoustic paths. Alternatively, individualized electroacoustic models can be used instead of fresh measurements, so to avoid the use of probe tubes during the calibration stage and cope at the same time with measurement uncertainty issues. During the second stage, called the control stage, it is assumed that the measured acoustic paths are time invariant. Hence, the audiological probe tube is removed, but the measured acoustic paths are incorporated in the ANC algorithm to make online approximations of the sound pressure at the eardrum. This is done by following a three-step approach. First, the estimated acoustic path B sub R is used to cancel the control signal at the position of the inner microphone, and through this, estimate the noise sound field at the inner microphone R. Using the estimated signal R hat, together with the microphone to eardrum acoustic path M, the noise sound field at the position of the eardrum D is estimated. Using the estimated signal D hat and the estimated secondary path S hat, an approximation of sound pressure at the eardrum E is done. The estimated signal E hat is then used to adapt the controller W, for instance, with the FX LMS adaptation algorithm. In this work, we consider an in-ear headphone equipped with 2 loudspeakers and 1 inner microphone, and propose an optimization procedure to compute the controller W, aiming at minimizing the sound pressure at the eardrum. The design procedure is based on the feedback virtual microphone arrangement approach proposed by Pavelczyk to estimate the sound pressure at the eardrum. In this approach, the estimated acoustic path B sub R is used to cancel the control signal at the position of the inner microphone, and through this estimate the noise sound field at the inner microphone R. Afterwards, the noise sound field at the inner microphone R and the eardrum sound pressure D are assumed to be equal. Using the estimated noise sound field at the eardrum D hat and the estimated secondary path S hat, the sound pressure at the eardrum E is estimated. The estimated sound pressure at the eardrum E hat is used now directly as input to a controller. Aiming at deriving the feedback ANC controller W, we formulate the PST of the sound pressure at the eardrum in terms of the signals and systems seen in the previous slide. In the equation, the left-hand addend determines the minimum achievable PST at the eardrum, which is 0 when the magnitude square coherence between D and R is equal to 1. The right-hand side addend defines the scope of optimization of the controller W. Here, the controller W and the estimated and real acoustic paths B sub R and S build a transfer function that should approximate the microphone to eardrum acoustic path phi sub dr divided by phi rr. When using the assumptions of the virtual microphone arrangement approach, the PST of the sound pressure at the eardrum simplifies to the expression seen at the right-hand side. Hence, the optimization requires only information about the secondary path and the PST of the noise sound field at the position of the inner microphone, phi sub r. The approach that we take is to use an FIR filter structure for the controller W and consider only one of both loudspeakers. Then, by using a modeled or measured secondary path S and a rough estimation of the PST phi sub r, we build a cost function that aims at minimizing the transfer function of the system by a maximization of the denominator of the PST of the sound pressure at the eardrum phi sub E. The optimization is then subject to a fixed impulse response length of 128 coefficients, a two constraint. First, a nominal stability constraint that is used to ensure that the controller yields a stable system, and second, a maximum amplification constraint that limits the so-called waterbed effect to a maximum amplification of 4 dBs. In the first experiment, we consider the tweeter loudspeaker of the closed Earpiece from the database by Denk and Kollmeier, marked here with a green arrow. We optimize the controller W using acoustic paths measured with a dummy head. As baseline, we consider another controller derived using an equivalent optimization procedure based on the classical minimum variance control approach, which aims at minimizing the sound pressure at the position of the inner microphone. We simulate a sound scene with a broadband diffuse noise field and the dummy head standing in free field while using the earpiece on the left ear. By subtracting the PST of the signal measured at the eardrum when ANC is on and off, the attenuation curve shown here in blue are calculated. Following the definition, when the attenuation curve goes below the 0 dB line, attenuation has been achieved, which is shown here as green areas. When the attenuation curve goes above the 0 dB line, amplification has been produced instead, which is shown as red areas. By looking at both attenuation curves, we can see that the attenuation of both controllers concentrate in the frequency region below the 1 kHz. This is a well-known limitation of feedback ANC systems caused by the delays introduced by the controller and the acoustic path between the inner microphone and the loudspeaker. Moreover, both controllers produce an amplification in the mid and high frequencies. This is the so-called waterbed effect of feedback systems, which says that an attenuation achieved in one frequency range produces an equivalent amplification in another frequency range. By comparing both attenuation curves, it is visually clear that the proposed optimization procedure achieves an attenuation that is approximately 12 dBs higher when compared to the classic optimization procedure. Moreover, an increment of attenuation bandwidth of approximated 550 Hz is achieved. This amplification produced by the waterbed effect in the mid frequencies remains under the specified maximum amplification of 4 dBs, until the 4 kHz frequency is reached. The uncontrolled amplification that occurs for frequencies higher than 4 kHz are produced in a frequency region where the closed earpiece already provides sufficient passive attenuation. In the second experiment, we consider the woofer loudspeaker of the closed earpiece, marked here with a red arrow. We optimize both controllers using acoustic paths related to the woofer loudspeaker. The acoustic scene is simulated again and the attenuation curves are recalculated. In this experiment, the improvement achieved by applying the proposed optimization procedure could be corroborated, but the attenuation in low frequencies became comparable between both approaches, with both controllers achieving roughly 20 dB of attenuation. Moreover, the improvement achieved by the proposed optimization procedure concentrates in the fact that a higher attenuation bandwidth is achieved. Also, an amplification of roughly 15 dB was measured, but in a frequency region where the earpiece already provides sufficient passive attenuation. Using the signals measured at the inner microphone and eardrum, it was found that for frequencies higher than 4 kHz, the assumption that the noise sound field at the inner microphone and eardrum positions are equal is not met for frequencies higher than 4 kHz. So, most probably the uncontrolled amplification can be traced to the unmet assumption during the optimization. We have come to the end of this presentation. Today, I have shown you an optimization approach to derive a feedback ANC controller aiming at minimizing the sound pressure at the eardrum. The optimization procedure is based on the virtual microphone arrangement approach, which requires models or measurements of the acoustic paths between the loudspeaker and the inner microphone and the eardrum. Using these acoustic paths, the controller is able to use a real-time approximation of the sound pressure at the eardrum as input. During the experiments, a higher attenuation could be achieved by using the proposed approach when compared to the classical approach. Moreover, the attenuation achieved at the eardrum is significantly increased in magnitude and bandwidth, both when using the tweeter or the woofer. However, the controllers derived with the proposed optimization procedure also produce higher amplifications in the higher frequencies. Nevertheless, these amplifications occur in a frequency region where the in-ear headphone already provides sufficient passive attenuation. So, this is all from my side. I'm looking forward to answering your questions. Bye!